We're taking a look here at part 4, and this is on page 71. And we're still continuing on now with the cells. We're talking about passive transport. And I'm going to show you a gross anatomy version of this where I've drawn a little picture of the heart here. As you can see, it's a little Valentine. And the heart pump. The heart is a muscular system that creates pressures. With each stroke volume of the heart, we get a stroke, and then we get a rest, and we get a stroke, and we get a rest. And on the stroke, we get usually somewhere in the vicinity of about 114 millimeters of mercury. On the rest, it drops down to about 75. The mean arterial pressure, if you take a third of the difference, 13, and add it to the 75, you get 88 millimeters of mercury. Sometime in 20B, I will be asking you to learn how to do that. But right now, I'm just doing it for you so you can see that's the mean arterial blood pressure. And we're coming down the arterial system here. We're coming down to a capillary bed. We're off in the tissue somewhere where we have metabolizing cells. Okay, so at this end of the capillary bed right here, you can see that we've diminished the mean arterial blood pressure to 55 millimeters of mercury. Over on this side, on the venous side, we drop off considerably to 10 millimeters of mercury, pressure out in each case. And then we have an osmotic pressure coming back in because there's so much protein in the blood, in which we have 25 millimeters of mercury, really pretty much constant osmotic pressure across the membrane here. Okay, so over at this end where the hydrostatic pressure or the blood pressure is greater, we're going to win, and we're going to be having filtration of nutrient-rich solutes and solvent coming out. There's water, there's oxygen, and then there's things that are dissolved and things that get transported across, but generally speaking, it's all dissolved and coming through. Okay, and then over here at this side, we have cells that have completed their metabolism, and they have CO2 and urea and other things to pass back. And because the pressure from the inside of the blood vessel is so low, that means the osmotic pressure is going to win, and we get the cleanup. Okay, we have capillary beds all over the place, so these cells are near the venous end of somebody's capillary system. These cells are over here by this venous side, but they're also next to an arterial side somewhere. So that's the gross anatomy. Here we are at the cellular anatomy. And we have something that I refer to then as tonicity. That's what we're supposed to be learning about in this part of the book here, and we're looking actually at page 71 for this. And so we have 3 different types of solutions here. One solution right here, this is the way a red blood cell is supposed to look. It's round. It's sort of dimpled in the middle where there used to be a nucleus, and there is one no longer. And so it looks like a little Necco wafer, and it's filled with hemoglobin. And this is the relaxed look of a red blood cell. And in this scenario, we have something that's referred to as the isotonic state. Isotonic means that the tonicity, or that is to say the electrolytes on one side of the membrane, has the same sort of osmotic force as the electrolytes on the inside. Okay, so that means that the movement of water across the membrane is more or less even in both directions. So the cell can take on nutrients, and it can also give out waste products. It can also signal in an outward direction if necessary. Okay, so that's the nature of the cell. These cells don't really signal very much, but they do need to have a certain sort of flexibility in their size. They have to be at this sort of isotonic state. Okay, then we can change the solution, and we'll change the dynamics of the membrane. So in this case, we have a solution that is going to be very high in electrolytes, and we call this one hypertonic. Hypertonic is sort of like your salad dressing. which is a lot spicier and saltier than water. Okay, so if you were to put your carrot sticks or your celery sticks into a solution like this, a hypertonic solution that might be very salty and spicy, then the water from inside the cells within the carrot or the celery will leave, and we'll get this shrunken sort of looking cell right here, where it's gone from this nice relaxed full state to this very shrunken size. It's diminished. The water has left. Okay? So then we move on to this scenario, in which here is our little dimpled red blood cell, and here's our red blood cell becoming very puffy and oversized and swollen. And we call this solution hypotonic, hypo meaning less than, and so we have less tonicity, hypotonic solution. So there's perhaps just water here, or there's water and very little electrolyte. And so the water is the water is moving from the outside and entering the cell. It's moving down its diffusion gradient, and the cell is becoming puffy and swollen. Okay? So that's that particular scenario. Then we move on to active processes, and we'll consider that next.